We're going with the last presentation of the morning, Team 15. They had a very interesting model that had a levitating magnet act as a bearing. Team 14, are you guys almost ready? Team 15?
Team
Are
15.
you guys almost ready?
We are ready. We are 100% ready.
Please stop.
So, good afternoon, everyone. We are Team 15, and our project is the Levitating Wind Turbine. Myself, my name is Derek Allen. This is Joshua Bowen. This is Haj Ogedi. This is Abdul Rahim Haj Ali, and this is Adrian Sorolla. So basically, our vision statement here was to design a bearing that eliminates friction. We wanted to eliminate mechanical friction because the components of a machine, the internal components of a machine, basically dictates the machine's efficiency. So the method we used is magnetic levitation technology in order to reduce the friction created by the bearing touching the axle. So what we expected to happen was for our machine, our levitating machine, to spin up faster, achieve higher RPMs, and spin for a longer time than the regular bearing. So what we did was we designed, fabricated, and tested and prototyped a 1 to 232 scale magnetic levitating turbine, just to analyze it against this normal turbine with sleeve bearing. All right, so what we wanted to prove was that the frictionless magnetic bearing will outdo or outperform the regular bearing. We designed both of them side by side to compare as a comparison for the magnetic against the frictional bearings, the traditional bearing. So a little bit of background about this. There are over 10,000 wind turbines in the state of Texas alone. There are over 225,000 worldwide. All turbines are built with huge bearings, and which consequently create friction. So now I'll pass it to my friend Adrian, which will.
Okay, so the bearing that we decided to choose as a comparison was a regular sleeve bearing or a bushing. We felt like this was the best bearing because it was analogous to our system in terms of usually a sleeve bearing has it's the shaft with the bearing, and there's a space usually taking lubrication, water, oil, or sometimes even dry, as is our case. And we felt like it also hit certain points that we wanted to address with our magnetic levitation bearing, such as in a sleeve bearing, it's always in contact with the axle, it always generates friction, and they require regular maintenance. So into the design phase of our project, we decided we needed to set some requirements to make sure that our project stayed within the scope of our idea. So these requirements were, it needed to be manufacturable, simple assembly, easy to operate, simple functionality, and easy storage. We also needed to set some constraints in order to test our design and make sure it was in the most efficient, as efficient as possible. These constraints were it needed to sit parallel to the wind direction with a maximum wind speed of 10 meters per second. It also could not be on a slope. It could not be on a surface with a slope of 5 degrees or higher. I'm going to pass it over to Josh here, who's going to talk about our conceptual development.
Good afternoon, everyone. So initially we came with 3 concepts. The first concept that we came with, it was initially a directional concept, experimental, to see what direction we wanted to take. It was very raw and basic, using like just natural magnets. The second concept, as you can see, was more advanced, using the plexiglass and the metal to create a more stable and more firm structure. Though it was bulky, we go on to the third concept, which we used wood, and we used neodymium magnets to increase the magnetic repulsion, and in results, increasing the elevation of the shaft compared to the magnetic base. Right here we have a more detailed concept, a more detailed, comprehensive view of the second prototype here, and what we want to take, important things that we want to take away from here is the magnetic coil and the roller that was added to produce electricity. On the third concept here, like we said, we used wood, which was lighter weight, but it was also stable, and we also added a generator that was designed by my colleague Hodge here to produce even more voltage from our generator and from our magnetic bearing.
So this in turn led to our final design, which is this right here. We went with a 3D printed material, PLA. It was a lot more lightweight than the wood, so thus the magnets on the bearing posts were able to push the axle up, and it was not as encumbered by the weight of the wooden axle. So with this less weight, it was a lot more stable in the pocket of the magnetism. And once we had our final design, it was time to test both designs against a regular, or time to test our design against a regular sleeve bearing. So we built two identical designs, and we employed sleeve bearings on one and our magnetic levitation system on the other. And we needed to start testing. But before we could start testing, we needed to do thorough analysis to back up our testing results. And Hodge will carry it.
Thank you, Adrian. So to perform our analysis, we needed to take some assumptions, and the three main ones were load, model, and temperature assumptions. For the wind assumption, we decided to go with the wind and axle load for the load, and then for the model, we decided to go with the bearing and axle as our model of focus. And then for temperature, we decided to go with the idea that the device will function in a room temperature environment. There were three forms of analysis we decided to perform. The first, under theoretical, was friction, energy balance, and stress analysis. Whereas when we did the experimental analysis, we did friction, voltage, and speed tests. And then when we did the simulations, we did an FEA analysis and a magnetic field analysis. Here under the theoretical analysis, you can see some of our calculations that helped us determine our efficiency, whereas we used the energy going in as our rotational kinetic energy, and then after noting the frictions in the bearing and then on the stabilizer, we're able to determine our energy output, which then led to our efficiency calculation for both bearings. For the efficiency of the regular bearing, we're able to determine an efficiency of 22.3%, and then for the efficiency of the maglev bearing, we're able to determine an efficiency of 48.7%. We needed something to compare to industry-wise, so we decided to go and find what they thought the percentage efficiency was, and then for the industry estimates annual output efficiency of 30 to 40%, but then most people have, in real world situations, have decided like really it's not that. It's actually, it varies from 15 to 30%. While the industry says that, we truly don't know. But then real world experiences have shown that it's actually between 15 to 30%. And then on our calculations, you can see that we got the regular to be in 22.3%, which was between the range. But the maglev, which I'm sure was not put into their calculations, was 48.7%. Here we performed the FEA analysis on the device to show, after we improved on the stabilizer and the design of it all, to see whether the device would hold after the load from the wind force and the axle load had been reflected on it. As you can see, it keeps a safety factor of 15 while staying in the constraint of the 10 meters per second wind speed that we decided to go with.
So this is a magnetic field analysis of our specific neodymium magnets that are attached to our design right now. We took advantage of these magnetic field lines right here. So the force that's pushing outwards is what's holding up the front bearing post of this axle. So in the constraint, in the design, we make sure that our front bearing post was being pushed directly up by the magnets. But we also took advantage of the forces here on our rear bearing post. So our neodymium magnets are effectively pushing the magnet attached to our axle back into the stabilizer to keep it stable and balanced, so that as it's spinning, it's not balancing on the magnets.
For the testing protocol, like I said earlier, we're going to do a friction test, a voltage test, and a speed test. And to do this, we need equipment. And then we decided to go with a tachometer for the RPMs, a voltmeter for the voltage, and then an air pump to induce speed. And then my teammate here is going to show you how we utilize all this.
Okay, so you can see that they're both going at a constant rate of speed, but when the wind comes to abruptly stop, the maglev continues to spin for approximately 10 seconds, as you can see here in the video. Now, doing a side-by-side comparison with the generation of electricity, you can simply see that the maximum voltage is 103 that we got from the maglev, and then from the sleeve bearing, we got a maximum of 55 millivolts. For testing, we came to the conclusion that we did meet our expectations when it came to the RPMs. The maglev was able to reach the RPMs at a quicker rate and continue to increase as it went along with a short period of time. For testing with the voltage, with the increasing in the RPMs, you're increasing the voltage also from the generator.
Thanks, Josh. So when it comes to marketing, actually our product can be marketed in several outlets, and that includes teacher catalog, educational teaching marketplace, hobby stores, and lab hardware stores, and things of this nature. After we determined our specific market, we wanted to come up with a price point, and that's actually when we went to vendors and we got quotes and invoices. And for this prototype, it cost us around $13,000 and $398, and that, of course, including paying 5 engineers. But for the final product, when we're mass producing 1,000, it would come up to around $183 to make 1 unit. We're planning on selling that for around $250, and that would give us a profit of $67. For our final product specifications, one of the most important specifications that we would like to emphasize was the speed, which is for the maglev was 1465 RPMs against 945 for the regular bearing, and voltage of almost 6 millivolts compared to 55.7. In conclusion, we were able to come up with a functioning prototype, and we achieved the goal that maglev bearing are more efficient than regular bearing due to the absence of friction, and we were also able to come up with a fabrication influence design and possibly a simple kit for educational purposes. Just like all other designs, for this one we believe that if we use a stainless steel frame, we'll have a more sturdy design, in addition to using higher powered magnets and active magnets instead of passive magnets. This brings us to the end of the presentation. We're open for questions and comments. Thank you.
Any questions so far? More doubts?
So, like, that thing spins, does it send any data out right now, or it's just raw mechanical?
So,
Like a lot of these, I know, like, if you buy a wind turbine for your house, right, then it's got all this data that has to come in, data line that gives you information about what's been captured.
so right now, what we're doing is we're taking raw data from outside equipment. Like we showed, we have the tachometer and things like that. That is a future improvement. We wanted to create an application where this can be used with an application.
Any other questions?
So I'm a little bit confused about what is the size of the product that you guys would sell. On that marketing slide that you had. What is the size of the actual turbine that you would sell? What's the application itself? Is
Well,
it a house or?
The application, no, it's not a house. Our application is mostly for educational purposes, and that's kind of where we would market it, because it shows a lot about electricity, magnetism. It has wind speed. It has FEA analysis. It has a lot of different things that you can gain, a lot of different knowledge that you can gain from our project.
Okay, because you guys did show the big turbines that you have,
Yes.
outside, so that's why it threw me out about what you guys were actually.
Yeah, we did. We wanted to do it at a scale size so that if we were to scale it up to larger turbines, we can comparably see the difference between a regular bearing that's located in the wind turbine as opposed to a magnetic bearing.
We also wanted something that could fit in the room.
And another question that I had is, on the testing that you did you change the wind direction? Because you had it looking at it in front, right? What happens when you go up and down or left and right? What happens to your vibration too? Because you could see that it vibrates quite a bit, and at some point you're going to have some changes on the performance?
Well, the second prototype we didn't have that problem, but then there were like pros and cons to putting it in this design, which was having it go higher because we didn't want it like having the chance of, you said, like vibrating. So with this, it's more of a lesser chance that it's going to be hitting the bottom magnet. But with the other one, because it's so close to it, and yes, we have constraints for where kind of wind speeds we want it to be, but sometimes you can't control the weather, you know.
That's the point.
Yeah,
Right?
the other thing too is we noticed during testing that the majority of our testing we did with air pumps that were throwing out a straight column of air, but as we scaled up the fans and we had a bigger column of air, it was a lot more stable as well, just because the column of air was coming and it was not directionally hitting the fan in any way.
Yeah, that exactly, that was my point, you know, if you did more testing, then you should show a little bit that you did under test conditions. And also because you guys said that you only had like a 5-degree slope, you know, on the installation, which could be fine, but then the wind changes and that doesn't mean anything anymore.
Right.
Yeah.
Right.
Yeah, right.
So my question is regarding the power. So in terms of the voltage, so what was the electrical power you generate?
The volt. Sorry, can you repeat that question again?
Yeah, electrical power. So you guys showed the voltage.
Okay.
How much power can you actually, so you guys make for education for so how much power can it generate?
Well, we didn't attach how do you say resistant or the electrical circuits to it to make it produce what we wanted in terms of power, but we did get what it was in terms of energy loss.
At this scale,
If you have voltage, you should know what the current is.
Yeah.
At this scale, it's not going to produce as much power, not even much power to produce a foam, but at a full scale, equivalent to the current wind turbines that are out in the field, it's able to produce. It will be able to produce more power.
I was curious how much does this one make power? Because when you get voltage information, so you should have current information.
Let's go to the efficiency calculation we had. There is a slide with all bunch of equations in there. Yeah. Right there. Simple, without going into the details. When you calculated the efficiency, what was your input and what was your output?
So the input can be seen there to be 0.69.
No, not that
No,
number.
he's asking
What is it?
What is? Oh, it is the rotational kinetic energy.
The input is rotational kinetic energy.
Yeah.
So, based on how fast it rotates.
Yeah, the RPM.
The mass. Okay, and the output?
The output, it was gotten from after we factored in the friction. So after adding and subtracting what the friction takes away from it, then that's how we got our output.
And that is a theoretical friction.
Yes.
Okay. And in the other side,
Yeah.
you did the same.
Yeah, but there for the maglev, then we didn't have to like add the factor in bearing friction.
So you took away that friction.
Yeah.
Right. The only friction that's present in the maglev is the
Stabilizer.
friction, the small
Yeah,
And it's
I,
very
I
minimal.
just want to get a feeling of where the efficiency came from.
Yeah.
Okay, move to the finite element analysis, please. What are you analyzing here? Load of what on what where?
So for the finite elemental analysis, we added an axial load of the wind power that was hitting the fan head on, and we also added a body load of the rotating axle as it was spinning, which gave us this pushing back on the stabilizer.
So wind is axially affecting,
Yes.
and the load is affecting sort of.
Yeah, rotational and then body load also. Yeah.
Okay. So this is the levitating.
Yes, this would be the levitating.
Yes.
And that's the load on the stabilizer at the back, which is loose. It's not really solid.
No, it's a rigid stabilizer.
It's rigid. It's just like when it pushes it, like depending on how much force it is, it might change a little bit, but it never exceeded 0
Well,
point.
if it was rigid, then you're holding the shaft at the end, but the assumption is not you're not
No,
holding.
it's not.
It's
It's not
just
holding.
friction.
It's a flexible joint.
Yeah.
And therefore, does this apply? That's the question. Because if you're not solid attached, does all this finite element analysis apply? Now you're not working in the regular force transmission from one element or one member to the other, or two force members or anything. You're working in a completely different world. So,
Well,
I'm just wondering, and I'm not saying this is bad.
right.
Just bringing to you the question: is this the right tool?
Well, we definitely understand. Well, to better understand your question, you're saying, is this the right tool to?
And is it giving you information that's useful for your design?
Okay, so basically, when we did the finite element analysis right here, we are basically analyzing this piece right here. So it's rigid attached to the base, and it's being pushed back. So when we looked at it, we wanted to understand what the stress analysis was in these joints right here.
The other thing we wanted to see also was from the really original concepts, we had a wooden square holding it. And we felt like we could make the design better while still achieving the same purposes as the ones from the wooden prototypes.
I'm not going to push this argument further, but think about your tools you're using. There is a whole different world where you are all flex. Now, what you learned in machine design doesn't apply exactly the same. There are lots of changes. You're in the fluid world, where inertia plays different and the force transmission plays different. Marketing point of view, what is the size of the problem in wind turbines? Is there something you found from the market that says, oh, these 240,000 wind turbines running around the world have this problem, and therefore levitating magnetism is the solution to it? Is there data from the market that you have that supports what you do?
Definitely. The levitating or the turbines that are currently in use are not as efficient. It's a wide-known fact that they're not as efficient, and they don't utilize all the wind energy that they take in. So our magnetic levitating turbine pretty much uses a lot more of the wind energy that it takes in to produce voltage.
So if I propose this design and I go to the scale of the actual wind turbine, is this competitive enough economically and technically?
So we were hoping that in future improvements, when we're using active bearings, active electromagnetic bearings, where they have controls and system controls, automatic controls that make sure that we're not relying on passive magnets and the balancing act basically. And all these controls, Hall effect sensors, everything is keeping the bearing in place. So we're hoping when you scale it up to this size, we could go somewhere around this route and prove that with some of these electromagnetic bearings.
Remember, the question is not the question whether it's going to work or not. It's to bring to you the thinking of to scale something up from whatever it is now and to be competitive. Aside from anything, just the simple math thinking is I'm going to have to break even or at least a little better in the price. And you're adding sensors and magnetism. Where am I going here? So I'm not saying this is bad. Don't worry about answering. I'm just saying multiple elements should be thought of as you do this, and more testing is needed. But go ahead, tell me what you needed to say.
Oh, I was just going to say, when you have any kind of mechanical parts, they're going to need to be refurbished or replaced after a while. With this type of design, it'll be very, very little replacement, very little maintenance needed over time. So I think you make some of your money back in maintenance.
But then, in a regular wind turbine, you don't feed power to get power. Now you're going to have to feed power to get power. In terms of sustainability and efficiency, I don't think you have an answer, but something to look at, because all sustainability elements, devices, ideas, people consider the fact, okay, I installed it, I'm getting the sun, I'm getting the wind, I'm getting energy. But they never consider the fact how much did it take to manufacture, how much pollution it made, and what is it going to do after it goes to the grave? Cradle to grave, the whole cycle. This is going to need power to run, right?
What, ours?
Yeah.
No. We made. Oh, I'm sorry. Go ahead, Josh.
Well, see, we made it this way because initially we wanted to get to the point to where it can produce power from the wind and the sensors and things of that sort can run off the power that it initially generates. So it's going to generate its own power and then power the sensors and the electromagnets as it produces the power.
Then we're going to push back and say, yes, you achieved efficiency in production, but you went back and consumed it in running your magnets. I don't think you did this calculation yet. It's still ahead. So think about it. But I think it's an aggressive idea, but it definitely has a lot of room to think and to do. Very good job.
Thank you.
Thank you, sir.
Any
Any
other
other
questions from the guy?
Thank you, guys.
10:15, thank you.